This section 3.1 is giving us some background that we'll need to start working with higher order equations. So we're going to start out like defining what that means for us, and then we'll have an initial value problem for this type of differential equation. And then we'll give the theorem that kind of tells us when we're guaranteed a solution, same way we did when we first learned about differential equations. And then after that, we'll move on to talking about forming what's called a fundamental solution set for this type of problem. There are going to be three parts of that: superposition, linear independence, and then thinking about what we need for non-homogeneous equations. So I know that I'm bringing back some vocab that we haven't thought about in a while. Don't worry about it. It's all going to become familiar as we work with it some more. So first up, we're just going to sort of define what we're working with here, which are going to be linear ODEs, so linear differential equations of nth order. So all during exam 1, you were working with first order differential equations. And an initial value problem for this type of equation is going to be given by the following. So we're going to have some function a sub n of x times the nth derivative of y with respect to x. And we can go down in derivatives. Eventually, you would be left with like a first order derivative, maybe something that just depends on y, and it can be equal to some function that depends on x. We'll call g of x. So when we were working with first order equations, we were only allowed to have first order derivatives, one derivative in every equation. Now we're just talking about nth order equations where you have lots of different derivatives. That's like a classification that we learned early on. Didn't have to worry about much because we only looked at first order equations, but this is when it starts to matter. And we're defining an initial value problem, so those always have those conditions that you plug in. You know, you're used to y at some point x being equal to some value for y. But the other thing that's going to change about this is that when we have higher order equations, we need more conditions. So for an nth order equation, instead of just defining y of x0, you have to define y of x0, its derivative, its next derivative, so on and so forth, until you get to the n minus 1th derivative. So just important to note here, an nth order IVP needs n initial conditions. And remember, those initial conditions in an initial value problem help us solve for unknown constants. So in order to solve for our unknown constants in this type of problem, we need lots of values to plug in. So that's the type of equation we're talking about. And then the first thing we're going to do is define another initial value problem theorem. So this is going to tell us something about existence and uniqueness. And the rules are going to be that if a sub n of x down through a sub 0 of x, so all these coefficient functions that you have attached to y and its derivatives, are continuous, and g of x is continuous, and a sub n of x is non-zero over some interval I, then when you start inside that interval with any x0, that would be the x value that we use for our initial conditions. If you start from that point, then a solution y of x to the initial value problem is unique. So this should feel kind of familiar to the first initial value problem theorem we learned, which also depended on the coefficients and the right-hand side being continuous. Just now we have many more coefficients, so more conditions that have to be met. Another thing that we can think about are what's called a boundary value problem. And we're not going to do this a whole lot. It's just sort of something that might come up in other classes, so we make sure to mention it here because it's sort of related to what we're talking about. But since we have multiple initial conditions, in our initial value problems, we can think about a related problem called a boundary value problem. Where we think about x sort of falling between a set of values a and b. And the boundary value problem would be sort of written as a differential equation first, just like our initial value problems always start with a differential equation. So here we have a second order differential equation. And then you'd have like y of a equal to y0. And we would need a second condition because this is a second order equation. But instead of having y prime of a equal to y1, sort of following the rules that we gave here, for a boundary value problem, what you'll say is that y at its boundary takes on a different value. And so all that we're doing is sort of giving our conditions over an interval instead of in terms of derivatives. But just because I wrote it this way with, with y's, you can still use derivatives if you want to. So for example, you could have y prime of a equal to y0, y prime of b equal to y1. That would be okay. That would still be a boundary value problem, even though it uses derivatives. What's going to be most important for us right now is that the initial value problem theorem doesn't work the same way for boundary value problems. So existence and uniqueness of an initial value problem does not guarantee existence and uniqueness of a similar boundary value problem. BVP is the abbreviation for boundary value problem, just like initial value problem is abbreviated IVP. So in the next video, we'll go ahead and do an example to become more familiar with these types of problems. So go ahead and proceed to that one.